Alright, here we go with iChem lesson number 22 on heat and chemical reactions. Essentially what we'll be doing today is understanding another reactant or product that is not really measurable or tangible, but you can feel it, and that is energy. So heat is a form of energy. First of all, energy is not matter, so we can't measure it in grams or moles or any of those kinds of things. Energy flows. The flow of energy into and out of a system can be involved with both physical and chemical changes. So adding or taking away energy happens with reactions or physical changes like melting and freezing and those kinds of things. Measuring the amount of energy flowing into and out of systems is often quite useful. And that measurement is done in the units of joules, which we abbreviate with a capital J, or calories, which we abbreviate CAL. This is actually not necessarily the same. It's not the same as the calories in your food. 1 calorie in our food, which would be in science a calorie with a capital C, is actually 1,000 calories, like these calories we're talking about here. So there are two heat changes and chemical changes. One of them has to do with, and when we went through reactions, indicators of reaction, we talked about changes in temperature. Getting colder or hotter is a heat associated with chemical reactions. Now, endothermic reactions, heat goes into the reaction, so it sort of behaves like a reactant. Heat goes in, behaves like a reactant, so that the surroundings will become cold. It's taking heat away from the surroundings. If you touched the outside of a beaker where an endothermic reaction was occurring, it would feel cold. And exothermic reaction is the opposite. Heat comes out of the reaction. Therefore, a heat is similar to a product, and the surroundings become hot. If we think back to the reaction we did last week, or earlier this week technically, with the magnesium and hydrochloric acid, if you felt the side of that flask, you felt that it got quite hot. So that was an exothermic reaction. You can represent these two things with a reaction curve. So in an endothermic reaction, we know that heat goes into the reaction, similar to a reactant. So heat is added to the system like a reactant. Heat goes in so that the potential energy of the reactants, the products here, is higher than the reactant. So products have a higher energy than the reactant. So energy has to be added for the reaction to occur. This piece up here, we're not really going to talk too much about it. It's called the activation energy. This means that even though for an exothermic reaction, where the energy of the products is lower than the energy of the reactants, heat goes out, is released, or in other words, heat is like a product. Energy still needs to be added for the reaction to be activated, for the reaction to start. So a way to think about this is fire. Fire doesn't just spontaneously happen, but combustion is an extremely exothermic reaction. It requires that spark, that initial spark in the beginning for the reaction to happen. That is the activation energy. If we're talking about the delta H value, the heat of reaction in words, we represent it as delta H in symbol. It is positive for endothermic and negative for exothermic. So just to reiterate here, in an endothermic reaction, heat is a reactant, or like a reactant. In an exothermic reaction, heat is like a product. And this will make more sense when we start looking about our reaction equations with heat. There are two ways that you will see a reaction equation with heat involved. One way will be just the plain old reaction equation like we've been seeing it, and then off to the side there'll be delta H equals blank. Okay. Another way, so this negative here, if we think about it, goes with an exothermic reaction. Remember that in an exothermic reaction, the heat can also be written as a product. So another way you'll see this is the reaction equation. Instead of delta H equals off to the side, heat will be written as another product, plus 791 kilojoules. This allows us to write a new conversion factor. So from this we can equation, and the good news about this is you have to be given a balanced equation along with it, because the balanced numbers are associated with this number. You can write three conversion factors. So I can say 791.4 kilojoules are formed for every 2 moles of sulfur reacted. I can say that 791.4 kilojoules of energy are released for every 3 moles of oxygen reacted. Or I can say 791.4 kilojoules are formed for every 2 moles of sulfur trioxide formed. Okay, so you can see where I'm getting at here. Now this becomes a conversion factor that allows us to convert from moles to energy and from energy to moles in our stoichiometry equations. So that's where we're going with this. Examples that we're going to work through are on the back of your viewing guide. So the first question is, how much heat will be released when 6.44 grams of sulfur reacts with excess oxygen? You're given on your paper the equation in this form. The one we talked about where it's written normal and then with delta H equals off to the side. A synonymous equation is this one. 2S plus 3O2 react to form 2SO3 plus 791.4 kilojoules as another product. These both tell us that energy is produced or released from the system. The negative indicates exothermic, which indicates energy is a reaction. So this is an exothermic reaction. So your surroundings would become hot. Okay, so to set up the stoichiometry, I start with my given. It tells me that sulfur is in excess, oxygen is in excess, so I know that that sulfur will be limiting, and I can start with that as my given to find my yield. So first I need to convert from grams of sulfur to moles of sulfur. So grams here, moles here. And then using the molar mass of sulfur, 32.07 grams per 1 mole. And now we're going to do something different than we've done before. Moles of sulfur is what I have right now. And what I want is energy, how much heat. That's kilojoules. So go back to your conversion factors that we just wrote. We want the conversion factor between kilojoules and moles of sulfur. It comes from my balanced equation. So I know that 791.4 kilojoules of sulfur are produced for every 2 kilojoules of energy rather, are produced for every 2 moles of sulfur reacted. If I plug all of this into my calculator, I should end up with 79.54 kilojoules, and then you can either say negative 79.54 kilojoules to indicate that it's released. I prefer you say indicate that it's released or produced by the reaction, to indicate you really understand what's going on. So 79.54 kilojoules are produced. Let's do one more. Okay, so this next one, I have another reaction. I have water reacting with carbon plus 131.4 kilojoules gives me carbon monoxide and hydrogen. Now, here it shows energy as a reactant. That means energy has to be added to the system, which means you have a endothermic reaction and a positive delta H. So we can write a synonymous equation where instead of writing the 131.4 kilojoules as a reactant, I can write it off to the side here. So, now, dimensional analysis. Start with my given. I'm starting with 1 metric ton, which it tells me is 1,000 kilograms of carbon, and I want to convert that to energy. Well, I don't use kilograms in my molar mass, I use grams, right? So first I want to convert to grams. 1,000 grams are in 1 kilogram. Now I want to convert from grams of carbon to moles of carbon. This is just the molar mass of carbon, 12.01 grams per 1 mole. Finally, I can convert from moles with my mole to energy ratio. Moles of carbon to kilojoules of energy. So come back to my equation. I have 1 mole of carbon reacts, and when 1 mole of carbon reacts, 131.4 kilojoules need to be added to the system. This is an endothermic reaction. So let me plug this into my calculator. I'll do 1,000 times 1,000 divided by 12.01 times 131.4. And I get a really, really, really big number. 1094082.6. This is kilojoules. It is a really, really, really big number, which makes sense because I'm talking about starting with kilograms of carbon. Okay, and then is it a reactant or a product? Is it added or taken away? It needs to be added. It's an endothermic reaction, so I need to qualify this. Added to the system. Okay, make sure you do your Google form and come to class prepared to solve more problems on Monday.